Hello, I'm Yuan from EPFL. Today, I want to talk about our paper, One-Way Functions versus TFNP, Simpler and Improved. This is a joint work with Lukáš, Mika, Pavel, and Gilbert. One of the mysteries in theoretical computer science is that there are many NP problems that are neither known to be in P nor known to be NP complete. For example, graph isomorphism, computing Nash equilibrium. The question is that can we further specify the hardness of these problems? Actually, there are already many different views of the region between P and NP complete. And in this talk, I will focus on two of them, crypto and TFNP. Let's begin with the most basic objects in cryptography called one-way functions. We say a function is one-way if it can be computed efficiently, but for any efficient adversary, the probability for adversary to invert the function is negligible. Now let's look at the crypto hierarchy. I only draw a very small part of hierarchy that contains some important primitives in the field. In this graph, if there's a solid arrow from primitive A to primitive B, that means we can build B from A. On the other hand, a dash arrow from A to B means that we cannot build B from A in a black box manner, and we will explain it later. And from this picture, we can see actually the crypto hierarchy is highly well understood because almost dash arrows almost appear everywhere. And the other hierarchy I want to mention today is the recently very popular TFNP hierarchy. Before showing it, let me define what is TFNP. So a search problem is defined by a relation. Given an input X, we want to find some solution Y such that XY is in the relation. And we say the search problem is total if for every input X, there exists some solution Y. And we say a search problem is TFNP if there exists efficient verifier that verify XY is indeed in the relation. Besides, for any input X, there must be some solution Y of polynomial length. For example, consider the search problem. Give an integer greater than 1. We want to find the prime divisor of the input. And the problem is total because any such integer must exist. And given some candidate solution, we can check in polynomial time that it is indeed a prime divisor of the input. Okay, now let's look at the TFNP hierarchy. Because it is known that TFNP is unlikely to have complete problems. So people define many subclasses of TFNP by defining their corresponding complete problems. For example, this PPP and the PWPP, they are classes that contains the complete problems which is finding collisions in an array. But these classes are different because the complete problems, the arrays in their complete problems have different shrinkage. And actually, many natural problems fit very well in this TFNP hierarchy. For example, Nash equilibrium is a p-pad complete problem. And this Ramsey problem is no easier than PWPP. And there are some also very interesting result about the relation between these TFNP hierarchies. For example, recent breakthrough shows that CLS is intersection of PLS and PPAD. And actually here, I didn't draw dash arrows because there are separations almost everywhere. Separations actually everywhere. And I also want to mention that this TFNP hierarchy is also closely related to proof system hierarchy in proof complexity. As we can see, both two hierarchies are very well understood. So what do we don't know about these two hierarchies? A natural question will be, can we put these two hierarchies together? Why we need two hierarchies? So let's just put these two hierarchies in one page. Actually, we can see there are some things already known. For example, the TFNP class PWPB is actually equivalent to the crypto primitive collision resistant hash functions. And the one-way permutation could be, and if one-way permutation exists, we will have PPP hardness, and we will see it later. It's a very simple reduction. On the negative side, it is known that the existence of one-way function cannot be based on p-pad hardness in a black box manner. And in this talk, I think we will focus on the question, a very interesting question, that can we construct some hard TFNP problem from one-way functions? And we show something negative. Before showing the result, I want to define the model. So black box reduction R from a primitive P to primitive Q is an algorithm that given the challenge, and this algorithm has oracle access to the hard function F and also has access to the solver S that solves primitive Q. Besides, the solver S also has oracle access to the hard function F. There are two things that we need to note. First, because the problem is a search problem, so the solver is not determined. Second, the reduction cannot use the code of F. It can just make oracle access to F. Okay, so now we can define this fully black box reduction. It is saying that for there exists some efficient reduction such that for every solver that solves primitive Q, the reduction with oracle access to the solver and the hard function will solve primitive P. So let's see the example. So I just want to quickly define this PPP and one-way permutation. So PPP is a set of search problems that's reducible to finding a collision in an array that maps from n+1 to n. And one-way permutation is similar to one-way function. The only difference is that the function needs to be a permutation. Okay, so now if we are given a one-way permutation challenge, how do we use the algorithm that solves PPP to solve this challenge? Well, given the challenge, we can construct a PPP instance by introducing another input and maps it to the challenge that we want to invert. And because we are given a permutation, so this will induce the only collision in the PPP instance. And by finding the collision, we can find the pre-image of Y. Okay, so now with the definition of fully black box reduction, I can define black box separation. So by taking the inverse of fully black box reduction, we have this fully black box separation. It's saying that for every efficient reduction, there exists some solver that such that the reduction does not solve the primitive P. And in this talk, we will focus on an even stronger notion of separation. So we switch the first two quantifiers, we will get this semi-black box separation. It is saying that there exists some universal solver such that for every reduction, the reduction does not solve the primitive P. Okay, so now we can apply it in our problem. So we want to find a TFNP solver S such that for every efficient reduction R, the probability that the reduction inverse F is negligible. And here, F is uniformly sampled from set of injective functions from n to 2n. And here's our result. We only show some restricted results. We show that there exists a universal TFNP solver S such that for every efficient reduction R, but the reduction R has following constraints. First, R only makes a single query to the solver. Second, R cannot make F queries before calling the solver. And with these constraints, we can show that the probability for R to invert the function is low. All right. Actually, there were some papers 3 years ago that prove something similar, but our paper has two more advantages. First, we rule out a broader class of semi-black box reduction. Second, our technique is new and much simpler, which produces a much shorter paper. Now I want to talk about our techniques. I will start by defining our TFNP solver. So we fix any TFNP instance together with the input X. So now the only variables or inputs to the TFNP solver can be just the random function F. And this function space, random function space can actually be approximated by a huge hypercube. And the verifiers can be seen as a collection of depth T decision trees, which query the variables in F. Okay, and we collect all this accepting leaf, and each accepting leaf corresponds to a with T conjunction. And because the TFNP instance is total, all these conjunctions will cover the whole function space. Okay, and our solver is actually very simple. It will just choose an ordering of the subcubes or conjunctions. And for each random injective function, we'll find the first subcube in the decision list, which contains the function, and we just return the solution with associated with it. Okay, for example, if the decision in this example, if decision list is in the order of blue, orange, red, and green, the solution returned by the solver will look like this. All right. So the next question is that how do we choose the ordering? We cannot arbitrarily choose the ordering because it will cause some problems. And a necessary condition is that the solver should have low leakage for every image. Okay, so we say a subcube leaks some image y if it fixes fx equals to y for some x. For example, this blue rectangle corresponds to f2 equals 3 and f4 equals 9. So it leaks two images, 3 and 9. And we want to return an ordering such that for every image, the probability of a random function whose solution leaks that image is negligible. And so next question is, how do we realize such solver? And it can actually be implemented by a simple greedy algorithm. Okay, here's realization of our solver. We maintain the leakage for each image, and we protect the image with leakage greater than some threshold. This will guarantee that the total number of protected images at any time is at most square root of n. And when the fraction of uncovered function is still not too small, let's say greater than this number, then we can find a subcube that covers at least one uncovered function. Second, it does not leak any protected images. So then we'll make some progress. And when the fraction of uncovered function is very low, when we can just choose an arbitrary order of the remaining subcubes. And this can be seen as the error term, but because it is too low, so it will not affect our result. Okay, so now let me briefly talk about correctness. So we have this low leakage TFNP solver plus our TFNP solver is a decision list. So we will have this stability lemma, which is saying that for every image y, if we sample a random function which does not contain y as an image, and we sample a random position, if we reroute fx to y, with high probability, the solver will return the same thing. And then we can apply a common technique in cryptography called game hopping to get what we want. Okay, finally, I want to talk about some further directions. First, our result is very restricted. So I want to see, can we prove some more general black box separations from one-way functions to TFNP, or even from one-way functions to some subclasses of TFNP, like PLS would be enough interesting. Second, I want to know that can we prove more reductions or separation between other crypto primitives and TFNP? And I think one particular interesting question is, does K agreement imply TFNP hardness? Okay, that's all of my presentation. Thank you.